Welcome back and happy Friday to everybody. Let's see, so we were talking last time about hybridization as a concept in valence bond theory for explaining geometry of atoms. So basically the reasoning starts out like this. Carbon's bonded to four things in methane because electron pairs like to be as far away as possible, and by symmetry, the geometry of methane needs to be tetrahedral. And we said the problem with that is just that if we're going to try to make bonds from atomic orbitals on each atom, that the p orbitals on carbon don't point in the right directions to get you bonds to make an individual bond with a hydrogen. So instead, what we do is we mathematically mix together all of the 2p orbitals and the 2s orbital, and we get four of these hybrid sp3 orbitals, and we said they're all oriented, the sp3 orbitals are oriented in a tetrahedral arrangement, and then we can conceive of making each bond in methane from overlap of the large lobe on one sp3 orbital with the 1s orbital on hydrogen. Okay, so a bond would be considered to be a lone pair in an orbital like this that envelops all of the space between carbon and hydrogen. But the key aspect of valence bond theory is a bond is two electrons between two nuclei. And this agrees very nicely with what you've been taught about drawing Lewis structures. We talked a little bit about antibonding orbitals, but we're going to leave that for a little bit later. Just understand that people that focus on valence bond theory mostly talk about bonding orbitals, and antibonding orbitals aren't that important. Okay? Now, let me just show you briefly. I hesitate to do it. It's kind of a pain, but I want to show you the MO theory picture of methane. This is not something I'm going to ask about on an exam, but it will demonstrate why what we finally come to and how we deal with molecules is useful, because this is going to be overwhelming. That's a ringing endorsement of today's lecture. So in molecular orbital theory, we drop the concept of bonds and we think of a molecule as having multiple molecular orbitals. These are orbitals that are delocalized across the whole molecule. And there's a set of rules for making these, which we don't need to go into. But you don't need any hybridization. You also actually don't need any concepts like resonance. And you basically let go of the concept of bonding, of a bond being two electrons. So where is the bond? And you say, yes, it's two electrons delocalized through the whole molecule. Let me show you what I mean by this. So you can construct these molecular orbitals through combinations of the available orbitals on each of the atoms in the molecule. All right, and same rule is going to apply. The alphabet of orbitals we have are 2s, 2px, 2py, 2pz. We don't care about the distinction between these, only that they're 90 degrees apart. And then you have four 1s orbitals on hydrogen. We're going to get four atomic orbitals in. We'll mix them together and get 8 atomic orbitals in. We're going to get 8 atomic orbitals out. We'll only talk about 4 of them. The easiest one to imagine is what would happen if you combined a 2s orbital on carbon with each of the 1s orbitals on hydrogen. You have to think of what I'm showing you here as a tetrahedral arrangement of the atoms. If it would be helpful, I can draw the lines like this, but remember, we're losing the concept of a bond. And if you imagine them all coming together with the same wave function sign, you can see that you would have an orbital that had continuous overlap between the carbon and all of the hydrogens. And in fact, you can see schematically what this, or I could draw a better representation of what this looks like if you did the calculations. It would look like sort of a continuous lobe of electron density surrounding, shoot, I need a bigger font there, surrounding the molecule. Okay, so that's easy enough. Well, which bond does this represent? Yes and no. Sorry, it doesn't represent a bond. It represents a pair of electrons delocalized across the whole molecule. And overall, we're going to end up with 4 pairs of electrons in an orbital like this. We call this a bonding molecular orbital because there is continuous overlap without a node between the carbon and each of the hydrogens. So even though it's just one electron pair, it would tend to pull the 2 nuclei together. All right, and this is basically what you get from the combination of the 2s with the 1s and the other 1s and the other 1s and the other 1s on hydrogen. Okay, so that's pretty straightforward. Now, how are we going to deal with the p orbitals? Well, to do this, it actually is helpful to look at a model of a tetrahedral carbon. I'm going to try to do this. You're going to need to get good at spatial reasoning with molecules on paper, seeing in your head what is on the paper. So what we're going to do is, this representation shows carbon-hydrogen bonds here and here in the plane of the page. This one's coming out towards you, that's a wedge. This one's going back into the page, that's a dash. Now, if we want, we can sort of do the steering wheel operation. This is not actually what I think the mathematicians call it, but we're just rotating. And if we do that, we'll see something like this. But to try to show you what that actually looks like and to show you where we're going with this, I'm just going to draw methane real quick. All right. So let's see if I can get it to the right perspective. Can you see how if you identify one plane as being the bond between, let me bring up notability again. One plane is made by these 3 atoms, and another plane is made by these 3 atoms, and those 2 planes are actually perpendicular to each other, right? And that should be, that creates a situation that p orbitals are actually good at. So let me show you how you make the other orbitals. Let's imagine that from this perspective of methane, we're going to take one of the p orbitals on carbon, and it's going to be in the plane of the page. It's going to be pointing up towards the top of the page and down towards the bottom. So this lobe of the p orbital is going to be in the same plane as those 2 hydrogens, so they could overlap with each other in phase, right? And then, of course, we're going to have a node at the nucleus, because that's what the p orbital is a node at the nucleus. And then we've got the other lobe here. Now, this lobe is still in the same plane as the p orbital, but imagine what we could do if that p orbital is sticking down towards the bottom. It can similarly overlap with these other hydrogens, okay? So all we have to do is bring these 2 hydrogens together toward that p orbital, and now we have a system where we have a large lobe of electron density. I'm going to try to represent this here, okay? So that's sort of one layer, and then down on the bottom side we have another layer. And again, it's hard to envision this in particular. You basically, it will be easier if I show you in the Spartan app. Yes, there we go. So that's sort of the situation we're looking at. You have red there is the same as our orange lobe in notability, and then perpendicular to it is the lobe on the bottom side, where the spot on the p orbital overlaps with the hydrogen that's in the front and in the back. Yeah?
That's one p orbital mixed with the 1s.
Yeah, so that's, if we sort of wrote it down, this would be one of the two p orbitals. And we would, I guess, add two 1s orbitals and subtract two other 1s orbitals to get the overall picture. This, what I just wrote here, is just to show what's combining in. It's not important, nor will I ask you to draw this. Okay, now you've got two other p orbitals that point in perpendicular directions, and we can make two additional molecular orbitals that look like this. All right? So, but in the end, we would, which of these orbitals, are these two orbitals the same in energy, or is one higher than the other? A couple of ways you can tell this, right? Look for nodes. This one has a node. Remember what that means? That means we're going through zero, the curvature of the wave function is higher, kinetic energy is higher. Also, there's a node at the nucleus, so potential energy is higher. And then look at the contributing atomic orbitals that we use to make this molecular orbital. This one comes from all s, this one comes from p and s. P is higher than s for reasons we've discussed before. So this is a lower energy one, and then this is a higher energy one. They are both bonding orbitals because electrons in these orbitals would spend time between nuclei, carbon and hydrogen, and tend to pull them together. All right? And as I said, we can generate, though I won't show you how, or you won't be responsible for it, 3 additional orbitals that involve the other. We can make, let's see, this is the one we drew. We can make 2 more that are equal in energy or degenerate to it with the other p orbitals and different pairs of hydrogens. Okay, and that's, we go through that in some detail in the MO theory study guide. The point is that if you use molecular orbital theory to describe methane, here's what you're going to come up with in terms of a prediction. You're going to predict that in terms of energy, you have one lower energy orbital, which is this one. And then, even though I haven't drawn them, or drawn more than just one of these, you're going to have 3 higher energy bonding orbitals that look like this. Okay? And then what we haven't shown in MO theory is that there are also 3 anti-bonding orbitals and 3 equal in energy anti-bonding orbitals that correspond to the minus combinations of these. And then there'll be a high energy anti-bonding orbital that's the minus combination of this. Now, for our discussion, we're not going to worry about these. Methane comes with 1, 2, 3, 4 pairs of electrons, so we can fill the bonding orbitals and none of the anti-bonding orbitals. And interestingly, this differs in the prediction that you're going to get from valence bond theory, which tells you you have 1, 2, 3, 4 equal pairs of electrons in methane. Okay? Which is accurate. It sort of depends on the experiment you do. And we're going to see that insights from valence bond and MO theory will be equally useful to us throughout this course. So we're going to develop a hybrid approach that I'm going to illustrate that's going to, for the most part with sigma bonds, use the familiar valence bond theory. But in cases of resonance where electrons can be delocalized, we're going to start to use some MO theory. And we're also going to remember the concept of an anti-bonding orbital like we saw with hydrogen. Sure.
So with your molecular orbital energy diagram, the lower energy level, that would be like, would that be just filled 1s, and then upper level is filled 2p3?
Well, yeah, the question is, does this, is this the 1s versus p orbitals? Remember that these are atomic orbitals mixed together to make a molecular orbital. So yes, this lower energy orbital does come from 2s orbital on carbon overlapping with 4 of the 1s orbitals on hydrogen. And then this comes from overlap of each of the p orbitals on carbon with the 4 1s orbitals on hydrogen. And if you sort of take a step back and squint, it doesn't actually look that different from an s orbital and a p orbital. It's sort of a similar type of pattern. Yeah?
So are these overlapped on each other in a real molecule like that?
Yeah, so the question is, do these orbitals occupy the same space in a molecule? Yes. How can they do that? Well, remember, electrons are waves, and waves are superimposable. Do you remember the guitar thing where I showed you that the primary harmonic tone was overlapped with the higher harmonic, and we could mute one without disturbing the other? And it's similar with electrons. Okay, so let's talk about the approach that the hybrid approach that we're going to take. And let's do this in the context of a slightly more complicated molecule, ethylene. I haven't said too much about antibonding orbitals yet, but what you learned from the antibonding orbital in hydrogen will be good enough for what we need to do today. So let's look at this. We'll just full send, as my children say. Is that still used in the modern parlance, or has that gone away? Ish. Depends on who. Yeah. Okay. My 14-year-old turns 15 tomorrow, and I promised him I would take him ski. He snowboards, I skis. I promised I would take him today. I'm not very good, and I'm worried he's going to encourage me to send it, and so hopefully I'll be here on Wednesday, not dead. Yes? Oh, why didn't somebody say something? You let me get 20 minutes into a lecture without lowering the screen? Don't do that. I am sorry. Wow. Okay. Very ashamed. Please interrupt me sooner. All right. Anything you want to see now that it's actually clear? Start from the beginning. Yeah. Okay. I've confirmed actually this time the lecture is indeed recording, so we should be able to go back and get stuff. Okay. So in our valence bond theory, MO theory hybrid, we're going to try to account for the sigma bonds really as just with hybrid orbitals on carbon and 1s orbitals on hydrogen. So we might say for this molecule that, for example, this bond between carbon and hydrogen comes from an sp2 type orbital on carbon with a 1s orbital on hydrogen. All right. Why does that carbon have to be sp2 hybridized? Because it's only surrounded by, here's the reasoning, it's only surrounded by 3 groups, therefore it must be trigonal planar. And the way we explain that is with hybridization, with sp2 hybridization. sp2 hybridized orbitals are going to look basically the same as sp3, only they should be a little bit more s. But we're going to still envision an sp3, a bond with an sp2 carbon and hydrogen as something that looks like this. Okay. And remember that for each bond that we make, we're going to consider that a high energy antibonding orbital exists. There we go. So this is the sigma bonding orbital we get from overlap of the sp2 orbital on carbon with a 1s orbital on hydrogen. we'll call that a carbon-hydrogen sigma bond. This is going to be a carbon-hydrogen, this is the minus combination, the carbon-hydrogen sigma star. This comes from subtracting the 1s orbital from hydrogen with the sp2 orbital from carbon instead of the other way around. And antibonding orbitals are going to look a lot like, conceptually, here's how you draw them. It may be helpful to continue to put the line there. Here is a dotted line that represents a node. Remember, a node is a place where wave function equals 0. And then on the either side of the node, we're going to have oppositely colored lobes. Let's see, and on the hydrogen side it looks like this, and on the carbon side it looks like that. Why is the lobe a little bit bigger on the back side of the carbon than towards the node? That's an issue that you don't really need to worry about, and I can't envision a situation where you might draw this in a different, as long as you get the colors correct, or rather the change in wave function sign correct, you should be okay there. That is an antibonding orbital, all right? And we're going to imagine that both of them are there, okay? And we're going to say that the sigma bonding orbital is filled, the antibonding orbital is not. So as we look at this molecule, we have 4 carbon-hydrogen sigma bonds, and therefore we have 4 carbon-hydrogen sigma bonding orbitals and 4 carbon-hydrogen sigma star orbitals. Now, in our hybrid approach, we're going to first deal with all of the orbitals that correspond to bonds in the molecule, and then we'll worry about how many electrons we have and which orbitals are filled versus not. All right? Let's deal with the carbon-carbon bonds. A carbon-carbon sigma bond, which I'm going to draw here, comes from overlap of 2 sp2 orbitals, one on one carbon, one on the other. And it looks much like you would expect for this situation. That is, here's a carbon, here's another carbon. You're going to get basically what you would get if you overlap the large lobes of 2 sp2 orbitals from carbon. So we're going to get a large amount of orbital in between the 2 nuclei and smaller lobes pointing away from the space between the 2 nuclei. Oops. And you can see we call this a sigma bond because if you rotate one carbon with respect to another, there's not any change in the overlap between those 2 orbitals. We would similarly have a carbon-carbon sigma star antibonding orbital. This is just the minus combination. Subtract 1 sp2 orbital on carbon with the other. Again, the antibonding orbital, which you can always recognize because it has a node between the 2 nuclei that you're talking about. Small lobes oriented towards the space between the 2 nuclei, large lobes oriented outward. They look like this because, remember, we're mixing 2 of the sp2 orbitals together, end-on-end overlap to give us this situation. So sigma and sigma star. Questions so far? Yeah.
On the second carbon, is there a hydrogen attached?
Yes, there is a hydrogen attached, and I forgot it, so that should have been listed up there. Yeah, the hydrogen was implied, but not shown, and I forgot about it. And where is this coming from? All right, 5 carbon-hydrogen sigma bonds, and similarly, we'll have 5 carbon-hydrogen sigma stars. Thank you. Yeah?
Which one of these is higher in energy?
Which one of these is higher in energy? So you tell me. Look at the nodes. Sigma star, because it's got one more node, and it's between the 2 nuclei. Yeah?
Is it okay to represent the carbon-hydrogen bond as large lobes slightly overlapping with the largest lobe?
Yeah, so I've just condensed that. You can do something like that, and that's fine. Yeah. Okay, so something that people generally ask at this stage is, how do I know what is the relative energy difference between carbon-carbon sigma bond and a carbon-hydrogen sigma bond. And there's two answers to that. One of those is really just to say, go look up the bond strength for a carbon-hydrogen sigma bond versus a carbon-carbon sigma bond, and that will tell you basically how much lower or higher each orbital is in relation to the other. In practice, it's not going to matter for our purposes. They're going to be similar in energy. So as we draw our MO diagram for this molecule, I'm going to list the sigma bonding orbitals, carbon, hydrogen, carbon, carbon, as all at the same sort of level. It's not actually that way, but for our purposes, it doesn't matter. Yeah?
So if you were to ask on a test, you'd have to give us the strengths if you really wanted us to differentiate.
Yeah, I would not ask you on a test which of these two is lower in energy. Yes? Yeah?
And in the study guide, it said like something about like C and X bonds, meaning like chlorine, bromine, iodine, stuff like that.
Yeah.
Are the 6 that are on the paper just the ones to know, or are there any more, like et
No.
cetera? So.
Right. So we'll talk about situations in which sigma bonds are not as stable, and therefore sigma bonds that aren't as stable have corresponding antibonding orbitals that are low in energy. We will talk about that, but I'm going to put that one off until just a little bit, if that's okay. What else? Yeah.
If we had only sigma bonds in the molecule and we had to choose the LUMO, would we have to differentiate between which anti-sigma bond or
Right. So yeah, the question is about, and if you've read the study guide, you know that we're going towards recognizing the highest occupied molecular orbital in a molecule because that's where the most reactive electrons are, and the lowest unoccupied molecular orbital because that's where something that has reactive electrons could interact. And what would you do in a situation where you have a hydrocarbon and everything's basically the same in energy for bonding orbitals and antibonding orbitals? The answer is that situation is boring, and so we won't worry about it. All right. Okay. So we've dealt with the sigma bonds. Now we need to deal with the pi bond and the lone pair. Okay. Now, you've noticed that I've drawn two resonance structures here. Let's talk about that for a minute. If you were just to look at this structure, what would you be tempted to say about this atom? What kind of hybridization would you call it? You might say sp3, right? Because it's surrounded by 4 groups, so you'd predict tetrahedral. All right. But resonance, the concept of resonance, tells you that there is a similar structure in which we can simply move these electrons over to make a pi bond, move these over to make a lone pair, and now the other one has the lone pair. All right, now you need to know one of the rules of resonance, which is electrons can be in different places, but nuclei cannot. Okay? If you don't master that, you are going to get questions wrong on the exam, and it will be painful for you because you will look back in retrospect and say, dang it, I knew that. So you are hereby warned. Resonance structures do not involve moving of nuclei, period. Now, envision what you would be saying. You'd say carbon 1 is sp2 hybridized here, and carbon 3 is sp3 hybridized. Those are two different shapes, right? Trigonal, planar, and tetrahedral. And then you come over here and say now 3 is trigonal planar and now 1 is tetrahedral. Can't be. Resonance is not hopping back and forth between two structures. Resonance is not moving of atoms. Going from flat to tetrahedral involves moving of atoms, right? It's sort of umbrella action. That can't happen, right? So if atom 1 is sp2 hybridized here, it must therefore be sp2 hybridized in the other resonance structure. Yeah?
How do you decide which one gets to stay?
How do you decide which one gets to stay? You have to know a little bit about pi bonds and then a little bit about resonance. So where does this carbon-carbon pi bond come from? I'm saying what atomic orbitals contribute to a carbon-carbon pi bond? Right, so presumably each of these sp2 hybridized carbons, we've accounted for the sp2 orbitals in the sigma bonds. What we have left is a p orbital. That p orbital is perpendicular to the page. It's coming out at you and it's below the page. I'm going to redraw this molecule and try to represent what we're saying here by showing that here's the lobe of the p orbital that's coming out towards you. Here is the lobe that's underneath the page. And then that can line up side by side with the p orbital that is on carbon atom 2. And what I'm drawing for you here is the plus combination. This is 2p plus 2p. If we viewed that from the side, it would look something like this. You've probably seen that before. This is side by side overlap. And so that kind of overlap is called pi type overlap. We're going to call this a pi bonding orbital. Notice that it's different because there's still a node. The nuclei are here. Here's where the carbons are. There is a node in the plane of the two carbons. So along the axis between the two carbons, there's no electron density. The electrons are above and below the plane, and they do span the space between the two nuclei, but they're not along the line in between them. Yeah?
So, from the reading, like from what I understand, isn't it that like the three carbons, they all have a lobe on either, like on
Yes.
the side?
Yeah.
All three of them are kind of like delocalized.
Yes.
Top and bottom.
Yeah, so this was just where does a pi bond come from, but you're noticing that on this adjacent atom, if it's going to be sp2 hybridized, that means that lone pair is similarly held in a p orbital that's perpendicular to the plane of the page, and you can see it has the potential to overlap side by side. Okay, so hopefully you're okay. You're pretty okay with a pi bond. Let's deal with the more complicated situation where we have 3 p orbitals on adjacent atoms, and we're going to mix them together, and we should get 3 new molecular orbitals out. Okay? Yes?
So the purple and the yellow represent different signs, correct?
That's right. Purple and yellow represent opposite signs of the wave function.
So why is it an attractive force between the purple and the purple and the yellow and the yellow and the pi bond?
Why is it an attractive force between purple, yellow, and yellow? Well, think of it as constructive wave interference instead of destructive interference. If the wave function went to 0 between the two nuclei, then the electrons aren't pulling the nuclei together. Let me show you what a pi bond actually looks like. Oops, we were already in there. Let's see. All right, so here is our flat trigonal planar molecule. I'm going to show you the pi bond. This comes from side-by-side overlap of 2 p orbitals. The colors here represent different wave function sign. Notice that this doesn't look like 2 separate p orbitals side by side. We've combined them together, right? And there's continuous same sign overlap on one side of the molecule and on the other side of the molecule. Does that help?
It's less of like a positive and negative attracting and more constructive and destructive.
Yeah, it's less about positive and negative attracting because the plus and minus isn't we're not talking about charge. It's about constructive versus destructive interference. Yeah.
So what we're looking at represents the pi bonding orbital.
That's right. This represents the pi bonding orbital. If you want to see the anti-bonding orbital, that's what it looks like. Notice the node in between the two nuclei where the wave function sign changes, not only in the plane of the carbons, which that node is there in the pi bond too, but now you have a perpendicular vertical sort of node that bisects the space between the two nuclei. That's the pi star or the pi antibonding orbital. All right. So normally, when we go through this, I would have gone sort of slowly through ethylene on its own and taken you through the pi and the pi star. Today, I've jumped straight ahead to dealing with resonance. Hopefully that's okay. I think the information in the study guide is decent enough to get you okay with the pi bond and the pi star. One thing that it would be useful to say, though, is to ask why the pi bond is higher in energy than any of the sigma bonds in the molecule. So we'll go back to Notability where you can see a drawing of a sigma bond versus a drawing of a pi bond. Okay? Any reasons why you would expect this to be higher in energy than a sigma bond? Go ahead. Has nodes where? Okay. Yes, the space between the two nuclei is occupied by a node in the pi bond, which means that means two things. First, the pi bond holds electrons farther from the nuclei. They're not spending as much space directly in between. Go ahead.
I was just going to say something about how when the electrons are further away from the nucleus itself, it takes more energy to take them away, and so they have higher energy.
Okay, yeah, potential energy increases as we go away from the nuclei. Also, the issue of kinetic energy, the fact that we have here a node between the two a node along the space between the two lines, does get us to change wave function more rapidly. Good. So we're going to see in general, pi bonds are higher in energy than sigma bonds. So if we're looking for the highest occupied molecular orbital and we have a molecule that has a pi bond in it, we already know we can ignore a lot of the sigma bonds and focus in on the pi bond. Okay. Now let's talk about what happens if you want to combine three p orbitals together. What we want to establish here is the connection between what valence bond theory tells you with resonance and what MO theory tells you, and how they basically give you the same conclusion. Let's review what valence bond theory says first. We would draw a hybrid structure for this molecule, which is generated by each of the resonance structures as contributors. If you look at resonance structure A versus B, both of them have double bond character between carbons 1 and 2 and between carbon 2 and 3. And then in the resonance structure A, the negative charge is on carbon 3, whereas in B it's on carbon 1. I'm just going to use lowercase Greek letter delta to represent a partial negative charge, maybe about 1/2 on either of those two atoms. Notice what the resonance structure tells us. Remember, none of these atoms are moving, but we have two electrons in a pi bond that are delocalized across the whole molecule. And then we have another two electrons represented by the lone pair, and they are simultaneously on 1 and 3, never on 2. Okay? Right. So now let's try to work out what the MO picture for this system of p orbitals that we're going to mix together. As we've done before, we're going to mix them together in all the combinations that make sense and obey certain symmetry rules. The study guide shows you how we generate these. I'm not going to ask you to generate pi orbitals from scratch on an exam. I will ask you to be able to rank them in energy and, given a certain situation, tell me which is the HOMO or the LUMO. But so don't panic if how you derive these orbitals isn't obvious. The lowest energy one is pretty easy, and I've already shown it to you here. This is what you get when you overlap the two p orbitals on atoms 1, 2, and 3, all with the same wave function sign. Schematically, if we looked at this from the side, we could draw the orbital like this. Here's each of the carbons. This is the plane of the sigma bond sigma bonds in the molecule going through the node on the carbons. We might also draw this as a continuous lobe of electron density above atoms 1, 2, and 3, with another continuous lobe of electron density below, where we have opposite wave function sign on either side. Okay, so that's, go ahead.
So when you do the load, does that use relation to just p orbitals?
So here,
The other one, on your right.
this one?
Yes.
This is what you get when you add the three p orbitals together in phase. Sometimes it's easier to tell what we're talking about when we draw a molecular orbital schematically like this. To me, this says, oh, that's a new pi orbital that I made from three p orbitals. It helps because it shows you the positions of the carbon. If you just draw this and don't have any positions of the carbons, I'm like, what is that? Is that a pi bond between two nuclei or more? So we're going to use both of these as ways to draw pi molecular orbitals. Yeah?
What do you mean by in phase?
In phase means with same wave function sign. Sorry about that. So this is the combination of three 2p orbitals with the same wave function sign. It's the all plus. Yeah?
So you consider that to be a homo configuration?
Not yet. So we're going to deal with which one is the HOMO versus the LUMO once we've constructed the orbitals and filled them up with the electrons. All right? Yes?
You would call that a single pi bond between three orbitals.
That's like a pi bond between three atoms. Yeah. Yeah, and notice we're dropping the idea that the electron has to be localized between two atoms. Now the other two orbitals that we can get, we're going to actually call this pi 1 because it's the lowest energy one. The other two that we can get come from, and I'm going to put atoms 1, 2, and 3 here. We can construct an orbital in which from the minus sort of combination of the p orbitals in which we have a node in between all of the nuclei. That's pretty straightforward, right? That's just the maximum number of nodes. Our pi 1 has 0 vertical nodes. This orbital here has 2 vertical nodes. So that gives you a hint that, and we're going to call this pi 3, that gives you a hint that there's something in the middle, pi 2, that has only 1 node. Now, if you think about the fact that this molecule is symmetric and that carbons 1 and 3 are basically equivalent, the molecular orbital we draw must also follow those symmetry rules. Why that has to be the case doesn't matter for this class. But the only way you can draw an orbital that has only 1 node is as follows, and that is to put the node on carbon 2. So I put the orbital on carbon 2, and then carbon 1 is here, 3 is here. And this will look as follows. Because there's a node in between carbons 2 and 3, the wave function sign has to be opposite on either side. Okay? And we'll call that pi 2. Now, hopefully, if I drew these three things and now asked you rank them in order of energy, you just do that by counting the vertical nodes, right? So you would see that pi 1 is the lowest energy pi orbital, pi 2 is next, then pi 3 in terms of energy. All right? Yes? Where would the sigma bonds be in terms of energy? Sigma bonds are always going to be lower than pi bonds. So if we wanted to include them in our diagram, which is now, we're going to have, I can't remember how many we decided, 5 carbon-hydrogen sigma bonds, 2 carbon-carbon sigma bonds, is that right? Yes-ish, okay. Now we're ready, now that we've ranked the orbitals, we're ready to talk about reactivity of the molecule by looking at electron pairs. Yeah, go ahead.
So with ranking these orbitals, they're all present at the same time. It's just the orientation, not how we're looking at it.
So we're ranking them in energy. The orbitals are all present at the same time because electrons are waves and they can overlap with each other. But we're using what we know about the relative energies of these orbitals to what we've talked about before about how sigma bonds are lower in energy than pi bonds to sort of rank the molecular orbitals. Because really the organic chemist wants to be able to look at a molecule, understanding what its structure is, and be able to predict where the reactive portions of the molecule are. Yeah?
Yeah, usually when we were combining orbitals, I kind of expected to see a lower energy orbital with a higher energy orbital. Like
Yes.
Anti-bonding and the bonding.
Yes.
I guess I was just I didn't expect to have a third option set just because we had three.
Yeah, the question is when we mix two together, it's pretty straightforward. One is minus, the other's plus. When we mix three, one goes lower, one goes higher. It turns out this one stays the same. This one is the same energy as just an isolated p orbital. Why is that the case? Well, because there's no situation here where two adjacent nuclei have electrons between them. So, and this is a minor point that we could just say a brief thing about. This pi1 is a bonding orbital, and you can tell it is because you've got overlap with same wave function sign across two or more nuclei. This is pi3 is an anti-bonding orbital, and you can tell it's that case because you've got opposite wave function sign between nuclei. And then this one we're going to simply, and this is not particularly important, but we're going to call it a non-bonding orbital because if electrons are in this orbital, they're not pulling atoms together, they're just on the end atoms. Yeah?
I'm just curious what happened to the orbital on the pi2.
Same.
What happens to the orbital here?
Yeah, on pi2, yeah.
Okay. You can think of it like this if you want. Why is there a node? So first of all, that is the molecular orbital. So there wasn't. So the idea that, well, where did the thing on carbon 2 go? The math tells you that the molecular orbital just isn't there. There happens to be a node coinciding with it. If you want a way to conceptually think about it, try to think about how you would take 3 p orbitals with only one node, right? You could do it like this, or you could do it like this. And if you add together those two possibilities, look at what happens. You'll get this on one side, this on the other side. Here, these two cancel each other out. Yeah, so that's one way to think of it. Okay, so now we can count the electrons that we have in the molecule, and we fill up each of the sigma bonds. I'm not going to count because presumably you can do that, and I want you to verify to yourself that this is the case, that the highest occupied molecular orbital is this pi2. And that corresponds, if you look, to what resonance told us. The most reactive electrons should be the ones associated with the negative charge, and they are on carbons 1 and 3, but never on 2. Similarly, the pi2 orbital is on carbons 1 and 3, but never on 2. Okay, you may be having an moment right there. If not, we need to get you there. And so we'll pick up next time with just a little bit more on this. I intended to finish chapter 1, MO theory, today. We're going to need another day on it.